So let's talk accelerating objects. So before we can really talk about acceleration, let's get some definitions out of the way. When we accelerate, we're going to be changing our velocity, so we're going to be using words like initial velocity, which is really just trying to tell you what your starting velocity is. We will denote initial velocity with a lowercase v and then a subscript of I for initial. And the unit is the same as it's been for velocity this whole time, meters per second. Final velocity is describing to you what your ending velocity is. So we will use a little v with a subscript of f to talk about final velocity. And again, it's just a velocity, so we'll measure it in meters per second. Average velocity. Now you guys are already familiar with average velocity from our last unit on constant velocity. We know that average velocity can be shown as a lowercase letter v with a bar over it. But now that we are accelerating, we actually have a new way that we could calculate average velocity, and that's by doing a mathematical average. 1/2 of the initial velocity plus the final velocity. But I've got a big caveat that goes along with that. This equation only works sometimes, not all the time. And that's a big thing in this class. I want to give you guys things that work all the time. But this is one that I'm going to put a star next to and tell you that this one only works if acceleration is uniform. And what do I mean by uniform acceleration? I mean that the acceleration is the same the whole time. We are not changing accelerations. We're not going from an acceleration to a constant velocity back to an acceleration or anything like that. It has to be the same acceleration the whole time. Otherwise, this equation doesn't work anymore. And again, velocity is measured in meters per second. Now, average acceleration is the rate of change of velocity. How much is your velocity changing every single second? We will use a lowercase a as a symbol for acceleration, and the unit for acceleration is how much your velocity is changing every single second. So we can look at that as meters per second, and that's a really wonderful unit because it reminds us what acceleration actually is. Changing velocity per time. But those of you who are big fans of math will recognize that this is an improper fraction, and we hate writing improper fractions. So if you were to rewrite this meters per second as a proper fraction, it ends up being written as meters per second squared. And that's where meters per second squared comes from. So let's draw a generic velocity versus time graph for an accelerating object. So maybe something like that. We have different parts of these graphs that we're always very interested in, one of which is the y-intercept. So our y-intercept right here tells us the initial velocity of the object. How about the slope? We always seem to look at the slopes of lines, right? So the slope of this line is trying to tell you what the acceleration is going to be. So if I give you a velocity versus time graph that looks like this, you can find the acceleration just by trying to find the slope of that line. And so if we were going to write a generic equation for a line like this that would work for anything, we remember that all of the equations in this class will take the form of y equals mx plus b. But again, we're not using the y's or the x's or the m's or the b's. We're writing what we actually have there. So in place of y, I would write final velocity is equal to my slope, which we just said was acceleration, multiplied by my x, and time is what is on my x-axis, plus my y-intercept, and we just said that the y-intercept was the initial velocity. So this is a generic equation that we could use in order to algebraically solve pretty much any problem. And to be a little bit more concise, we can write this as VF equals A delta T plus VI. And this is going to be one of our major kinematics equations that I ask you to memorize and I ask you to use whenever I ask you to solve a problem using algebra. But before we start doing a lot of things with algebra, we're going to be looking at some graphs because we can always solve problems using a graph. Now, we have seen position versus time graphs and we have seen velocity versus time graphs last unit in our investigation on constant velocity. But these graphs are going to look a little bit different now that we've got accelerating objects, and it's good to remind ourselves what the different parts of the graph mean. We're always interested in looking at the y-intercept of a graph, the slope of a graph, and the area of a graph. But the meanings of those three things change whether we are looking at a position versus time graph or a velocity versus time graph. So on a position versus time graph, the y-intercept is trying to tell us the initial position of the object. The slope of that graph tells us the velocity of the object. And then the area, now I don't know if you guys know what I mean when I say tell me what the area of a graph means. Now if I draw just a generic position versus time graph, maybe for something that's not moving, when I ask you to tell me what the area is, I'm really asking you to shade in the area between your line and the x-axis and tell me what does that area mean. Now this is just a rectangle, and a rectangle is base times height. So the thing that we are looking at here would have a unit of a meter multiplied by a second, because that is the units of our base and our height. But we don't know what a meter times a second is. That doesn't mean anything. A length times a time? That's bunk. So for a position versus time graph, the area doesn't mean anything. We don't care about the areas of a position versus time graph. Switching over and looking at a velocity versus time graph, all three of these things are very meaningful for us. We know that the y-intercept tells us about the initial velocity of the object. We know that the slope tells us the acceleration of the object. And the area here is a meter per second times a second. It's just a meter. So we know that the area will tell us what the displacement of the object is. Now this is a very nice place for you to refer back to anytime you're looking at a graph, just to make sure that you're reading it right. And let's get some practice reading these graphs. Now it's a little bit hard to see, but there are scales on these graphs. They go by ones. Every dot is a 1. What we want to do is we want to find the distance traveled between 0 and 2 seconds. So between 0 and 2 seconds is right here on our graph. And since this is a position versus time graph, that's telling us that we've stayed at a position of 5 the entire time. If we stayed at 5 the whole time, we went 0 meters. We got that by reading the y-axis. Now we want to find the velocity between 9 and 15 seconds. So 9 is about right there, 15 is right there. So we're talking about this part of the motion. Now velocity is the slope of a position versus time graph, so I just have to figure out what is the slope of this line. I don't exactly know what coordinate that is, but I definitely know what coordinate that is. This definitely seems to be 8, 8. This coordinate seems to be 15, 0. So let's do our good old y2 minus y1 over x2 minus x1 to figure out the slope. So 15 minus 8 over 0 minus 8. That should give us our slope. So 15 minus 8, that is positive 7. 0 minus 8 is negative 8. The slope of this looks to be negative. I think I don't have this correct in my notes. So let's do this really fast on the calculator. 7 divided by 8. Did I do this correctly? No, I didn't. Because between 8 and 15, that's 7 seconds, right? I don't think I did this correctly. This point is definitely 8, 8. This point is 15, 0. So 15 minus 8 is 7. 0 minus 8 is definitely negative 8. Yeah, okay. Negative 7, 8. I'm not so sure about this. Okay, thanks for bearing with me. I found my mistake. We need to do the y's first. Y's are 0 minus 8, and then our x's are 15 minus 8. That sounds like that's correct. So we get negative 8 divided by 7, and then if we turn to our calculator and do negative 8 divided by 7, we end up getting negative 1.14 meters per second, and that is what our slope is, which is what our velocity is. So we found the answer to this question using the slope of the graph. And then we want to find the velocity between 5 and 8 seconds. So 5 seconds is right here, 8 seconds is right there. We want to know the slope of that part of the motion, since the slope of a position versus time graph tells us velocity. And you know what? I don't need to do the slope formula. That looks like 0 meters per second to me. Let's go to velocity versus time graph. So again, it's kind of hard to see, but there is a scale here. This is 5, this is 10, this is 15. Over here, this is 5, and this is 10. Now we're looking at a velocity versus time graph, and I want to know what is the displacement between 0 and 3 seconds. So from 0 to 3 seconds is this part of the motion. And we know that to find displacement on a velocity versus time graph, we have to look at the area. So let's shade in the part of the graph that should tell us that displacement right there. So that looks like a box. We just have to do length times width. So it appears that the length is 3 seconds. The width is 4 meters per second. So altogether, we must go 12 meters. And again, we found that by looking at the area. Find the acceleration between 3 and 6 seconds. So from 3 seconds to 6 seconds, that's this part of the motion. We need to find the acceleration. And we know that we can find acceleration from the slope of velocity versus time graph. So let's see. This point looks like it is 3, 4. This point looks like it is 6, 7. So if we do y2 minus y1, 7 minus 4, over x2 minus x1, 6 minus 3, we end up getting 3 over 3. Our acceleration appears to be 1 meter per second squared, which we found by looking at the slope of the graph. When does the maximum speed occur? So if we look at this velocity versus time graph, wherever the largest velocity is, should just be the maximum speed. So we're looking for the portion of the graph that is the highest on the y-axis. And it looks like all of these points are the highest points on our graph. And so those points are at 7 meters per second. That was our greatest speed. We were at that speed from 6 to what appears to be 11 seconds. To get this answer, we read the y-axis. And now the last problem, find the displacement between 3 and 6 seconds. So between 3 and 6 seconds, We're literally looking at this area right here. And that looks like a trapezoid. Now, I like to break up trapezoids into a rectangle and a triangle because that helps me think about it. And I definitely remember how to find the area of a rectangle and how to find the area of a triangle. I can just add those two together. So it looks like my rectangle is 4 meters per second by 3 seconds. And it looks like my triangle is 3 meters per second by 3 seconds, and that's going to be divided by 2 since it's a triangle. And altogether, that means that my displacement must be 16.5 meters, which again, we found by looking at the area. All right, one last thing, and then you'll be done with notes for today. Last thing about graphs. We now have 3 different kinds of graphs that we can draw. We can draw a position versus time graph, we can draw a velocity versus time graph, we can draw an acceleration versus time graph. We only need to know one of these graphs in order to draw the other 3. So I would like for you to draw the corresponding velocity versus time and acceleration versus time graphs for the given position versus time graph. Now, it's easiest to draw them just down, so starting with position, go to velocity, go to acceleration. So we have to ask ourselves, what part of a position versus time graph tells us about velocity? It's the slope. So by looking at the slope of this position versus time graph, we can draw the velocity versus time graph. Now this is a curve, so it's hard to tell what the slope is at any individual point. But what you guys can do is you can draw little tangent lines to that curve and look at what the slope of the tangent line is doing. Now at the very beginning, our tangent line looks like it has a slope of 0, which tells us that our velocity must start at 0. And as we move on in time, these tangent lines have a steeper and steeper positive slope, which means that our velocity must be getting bigger and bigger. So we end up with a velocity versus time graph that is a straight line with a positive slope. To draw the acceleration versus time graph, we can look at the velocity versus time graph and ask ourselves, what part of a velocity versus time graph tells us about acceleration? It is the slope. What is the slope of this line? Well, it is a positive slope that never changes. Thus, we must have a positive acceleration that never changes. So it's a horizontal line in the positive area. Now, we used the slope of this graph in order to draw the next graph, and then we use the slope of the velocity versus time graph to draw the acceleration versus time graph. And that's really how it goes. We need to use the slope of one in order to help us draw the next. Let's practice that with the second one. We'll start by drawing some little tangent lines on this curve. And the tangent lines appear to start with a very, very steep positive velocity. That tells me that I must start with a very, very large positive velocity. Now, as these tangent lines move on, they become less and less steep until finally at the end it looks like we have a slope of 0 for our tangent line. So that tells me that my velocity is getting smaller and smaller until I finally have a velocity of 0 at the very end. Now if we look at this slope of the velocity versus time graph to get the acceleration, this slope is negative and it never changes, so we must have a negative unchanging acceleration. So again, we get a horizontal line. This time it's in the negative area. I want to tell you a few things. Number one, the craziest shape you may see for a position versus time graph in this class, the craziest shape you're ever going to see is a curve. I promise you I will not give you anything stranger than a curve. No loop-de-loops, nothing that tracks back on itself, just curves. The craziest thing that you are going to see on a position versus time graph is a sloped line. You'll never see a curve on a velocity versus time graph in this class. And then the craziest thing that you will ever see on a position versus time graph in this class is going to be not a horizontal line, a horizontal line. You will never even see something with a positive or negative slope. You'll just see a horizontal line. And the reason why is because the boundaries of this class is that we just go up to uniform acceleration. We don't do things like jerk or something where our acceleration changes. So this is the craziest stuff that you will see in this class. Last thing I want to say is about speeding up and slowing down. Speeding up and slowing down, when you're looking at a graph, it's best to look at the velocity versus time graph. If your velocity is getting farther and farther away from zero, you know that you are speeding up. If your velocity is getting closer and closer to zero, you know that you are slowing down. Whether you are speeding up or slowing down really depends on whether your velocity is getting farther away from zero or closer to zero. Lots of people try to look at the acceleration versus time graph in order to answer that question, but that's a fool's errand. You really need to look at the velocity versus time graph for that answer, okay? Good luck reading those graphs for accelerating objects.